Kamash, Radu, Victor, it's good to see you all. Hello. We're going to get started at about 11:05. So if anybody needs any coffee or anything like that, go grab it. Before we get moving, anybody interested in being a scribe today? Or would anybody like to lead the meeting? If nobody would like to lead, I'm happy to. Or if somebody would like to lead, I'm happy to be a scribe as well. Okay.
I can be a scribe if you'd like.
Victor, you are so kind. Thank you. Okay, it looks like we are at 11:05. Since no one has volunteered, I will volunteer to lead the meeting. So welcome everyone. I'm David Justice. You are here at this instance of the CNCF Tag Runtime Wasm Working Group. We are a CNCF sub-project working under Tag Runtime, and we follow the CNCF Code of Conduct, which generally means be nice to each other. Please raise your hand, you will be recognized. And please, let's have some fun and be nice. Awesome. So in today's meeting, we have two agenda items on the menu. Max and Marshall have joined us from Zed to talk about the component model usage in Zed and their experience thus far. It's really cool stuff. I'm super excited. Thank you all for joining us. It's really great to see you all. We're also joined with Tomasz et al. With, I believe, Till, Victor, and Guy, who are going to talk about StarlingMonkey, JSTS, and the impact to the Wasm ecosystem there. So thank you all for joining us today. Without further ado, I will leave it to Max and Marshall. I'm going to try to keep it to roughly about 20 minutes, guys, if that's okay. You don't have to take up the whole time. You can take up as much as you want, and then we'll have a little bit of Q&A, and then we'll shift over to the next one. All right, gentlemen, welcome.
Yes, thanks for having us.
Yeah, thanks for inviting us, David. Take it away, Marshall.
Yeah, so I don't really have like a bunch of structure. I think I'll start by just kind of giving like a broad overview and like a kind of high level summary of how we're using Wasm, what our experience has been so far, and then happy to like, take any questions if people are interested in like our experience with it or just, want to know more. So Zed went open source a year ago in January, and sort of shortly after that, we realized that we had a need to bring in an extension system because after going open source, we were having like PRs left and right of people wanting to add support for like every language under the sun into Zed. And so Max and I, we were the ones who worked on this new extension system. And so initially we were kind of doing it in a more like declarative fashion. So the first thing we wanted to add support for was languages like just syntax highlighting and like structural things using tree sitter grammars. And so tree sitter already supported compiling grammars to Wasm. And so we like our first version of extensions were just, in your extension.toml, you would say, here's how, or like, here's the tree setter grammar we want to use this commit, and we would build it to Wasm and then load it. And so we weren't doing anything, sort of executing code in Wasm other than, these tree setter grammars. And so that was sort of the first bit. And then we realized, okay, we need to also allow languages to expose language servers and, be able to like download the language server binary and like put it in the right place and start it up. And so that's when we realized, okay, we actually need, some form of programmability for our extensions. And so we initially started looking at, embedding a JS runtime and using that. But none of us, we write Rust. We don't really want to write JavaScript. And so then Max had the idea to kind of revisit using Wasm again, because there have been like some previous explorations, but the ecosystem was kind of too nascent at the time to sort of be useful. And so we took another look at Wasm, and I think that there had just recently been like a release, like a new Wasm time release, and it's sort of like, the stars all aligned. And so we were able to kind of find everything that we needed in like the current state of the Wasm ecosystem that we, wouldn't have been able to if we'd done this project like a month before or 2 months before. Yes, let's see. Am I able to share screen? I'd love to kind of just show some code here. Let's see. Oh, sorry, I need to grant Zoom access here.
Yeah, while Marshall's doing that, I'll add some like color to our sort of backstory. I think when we first started exploring extensions in Zed, we were kind of using Wasm. We really wanted to use Wasm the whole time, but we had someone on our team tried using Wasm modules and kind of building our own ABI for doing extensions and passing things back and forth as JSON objects that we'd like serialize manually into the Wasm heap. And then, like Marshall said, when we finally, after open sourcing, we finally realized the urgent need to do programmable extensions. I think was the month that Wasm, I don't know, remember the version of Wasm time that initially enabled the component model by default, but it had just come out. And so it kind of happened just in time. And we said, okay, like let's try Wasm components one more time. Back to you, Marshall. Looks like you got the screen share up.
Yeah, so here's sort of our like entry point into our extension API. So we have a Rust crate that all of the consumers use. And so internally we're using WIT-bindgen to like generate all the bindings. And some of those we like expose directly. So like here we're, re-exporting a bunch of these symbols that are coming directly from WIT-bindgen. But then there's also some other stuff that we sort of put wrappers around to kind of provide a more idiomatic Rust experience.
This is the guest side trait, right, Marshall?
This is the guest side of the component model. And so we have our own extension trait, and this kind of implements, this is just a regular Rust trait, implements basically these hooks that map onto like the exports in our Wasm world. And then what we do here is, a bit of magic where we like, store this kind of mutable this mutable static of that extension trait. And then what we do is we actually implement the Wasm guest and sort of delegate to that global instance. And so when we, load the extension, we like initialize that. And then on the host side, we're like calling into this global instance of the extension. And so we have, a number of different versions of our extension API every time we've made breaking changes. And I'll go a bit more into our versioning scheme later and how we like deal with that. But basically we have like copies of every single like major version of our extension API so far. And you can see we kind of started off like very simple. Like we have, this extension world has like a number of like different imports and as well as like a couple of exports. And it's for the most part, everything lives in this single like extension .wit. But then you can see in the current version we're working on, we now have, a bunch more. We've kind of broken it up into a bunch of different like modules, so that because we found that that actually makes them easier to version, because if you make a breaking change in one module, we don't have to like re-implement that, like re-implement everything. We can just like re-implement the bindings for that. And so then on the host side, what we actually do is, so we maintain, backwards compatibility for previous versions of our extension API. And so the main entry point is we have this like extension enum, which is holding, a different, extension kind of for each different version. And these are, generated using WIT-bindgen on the host. And then what we do is, again, we kind of have this sort of unified API. So, if we want to, start a language server, like on the host side, we'll call into this, and then we figure out like, okay, what version of the extension API are we using? And then we call the appropriate bindings there. And so we can like look at, so we'll like look at the previous version of our extension API here. So you can see we're using Wasm time component bindgen here. This like points to the WIT files that are in our like our extension API crate, and then so we're using the with functionality here to actually reuse kind of all the things that haven't changed between versions. And so this has allowed us to kind of reuse a lot of code and sort of reduce the amount of churn that we need to do every time we have to make a breaking change. There's still like a decent amount of code that needs like boilerplatey stuff that needs to be done. Like we have to have a bunch of from impls to kind of, because even though the representation in like the WIT is the same, and because like because we're using two separate bindgen invocations, they're actually like different types at like in the type system. And so in some cases we need to like use from impls so that we can like convert between things. Let's see. So yeah, we're using we use resources in like the component model to like expose some of our kind of like core Z primitives in the WIT. So like if we go and look here, like extension.wit, we have a resource work tree. Yeah, so like in Z we have the concept of a work tree, which is like like a group of files in your project, and so we expose that as like a resource, and so that allows the extensions to do things like get the contents of a particular file in the work tree as text, and then we're actually able to on the host side cheaply implement this rather than having to like serialize the entire work tree over the wire, which is very, very nice. Yeah, does anyone have any specific questions that they want to hear about our experience, or like how we're using Wasm, the component model? Yes, David.
Thank you, Marshall. So, I guess what was the biggest challenge, and what was the biggest benefit that you found?
Let's see. I think one of the bigger challenges was just during the implementation phase. Like we found ourselves doing a lot of digging inside of the like the Wasm time source code, and like basically trying to get things to work the way that we wanted to. I think like using the different bindgen macros, which were very useful, but it was like sometimes we couldn't figure out like exactly which of the features we needed to use of the macro in order to do what we wanted. Like like when we first started out and kind of we had like our first version, and we realized we wanted to make a breaking change, and so we were trying to figure out like, okay, how do we like structure this in such a way that things can be done kind of in a backwards compatible fashion. and we like, don't break the entire world every time we have to change the extension API. Like our first attempt at that was really just like we had, two completely like separate copies that were almost identical with a couple of changes, and we had to do a lot of like conversion. And then, that's when we figured out like, oh, we can use like, these like the with directive to kind of like basically like point a particular like, interface at like another version as long as they're, compatible. And then that allows them to actually kind of reuse the same types like from on the Rust side. And so that was like kind of a big breakthrough for us, but it was just something that we sort of had to figure out by like doing a lot of spelunking, because there also weren't a lot of examples of people doing like the exact sort of things that we were. It felt like we were kind of on the bleeding edge of things. Max, do you have any thoughts you want to add there?
Yeah, I would say that like backward compatibility is at the same time one of the things I'm most happy with that we've achieved, because like I don't know, I've worked on other plugin systems where everything's much more duck typed, and I love how there's just a like static typing all the way from Rust to the component ABI, but it was like quite a bit of a process for us to figure out how to do that in a way that didn't duplicate all the code. We still are duplicating some code. I also think just the general like mental model of WIT files was bye Frank was for me took a while to ramp up on what a world was. That was and like whether files had semantics or not, or whether it was like directories like had a significance in WIT, and like how basically it comes down to like how the component bind gen model works. And we sort of, I would say we arrived at a working setup that we can now just like crib, but I don't feel like I left it with like a very crystal clear mental model of like why WIT is the way it is. And I feel like there's WIT features that we're not using, like the versioning feature of WIT itself that maybe we could be using, and we tried to use, but we weren't able to like on our first attempt get to do what we wanted to do. So we sort of went with this approach that Marshall described, where it's a bit more manual, the versioning. But at the same time, like I said, what it lets us do, even though it's a lot of boilerplate, when like Marshall showed that enum where we like, if it's a version since 02, we call this method, it's still like very clear. And I love how safe it is, despite the boilerplate.
Yeah, I think, another thing that we sort of ran up against, like that we had to figure out was, how to actually kind of build against the component model. Cause I know there's like I forget what it's called, but there's like a CLI that kind of like, allows you to sort of build, Wasm bundle using the component model. And so we like were initially exploring that, but then we realized it kind of wasn't doing exactly what we needed. And so we ended up digging into the source for that to figure out like what it was doing. And so then so we have like our own like extension builder that we use. We like distribute a separate like binary that we use like in our GitHub repo for like, oh yes, cargo component, that's the one. So yeah, we have like our own CLI that we use like in our extension CI for actually building people's extensions, like building up the WASM and then distributing them. And then we use that same one also in Z itself. Like if you're developing an extension, you use kind of that same tool chain. And so we like, we build. So here you can see where we like, do a cargo build and we compile it to WASM, and then we actually use the component encoder that's coming from WIT component. And so then we use that to like, build it into like the WASM component model bundle. And then we actually do a couple we like actually go in and manipulate the WASM bytes a bit. So we like strip custom sections, I think, to get some size back. And then we also we like embed our extension version kind of in the bytes of the WASM bundle, so that we're able to kind of statically like look at like when we load a WASM bundle, we kind of look for this section that we've added that contains this WASM extension version. So and that's how we know which version of the extension API we need to load this extension against.
Come on, I know there's got to be more questions out there. Let's go, folks.
What do you think? So, before asking my question, I have been sort of quietly observing this for a while, and I think it's very exciting. And one of the things us working in the component model have been hoping for a long time is that it would be used in exactly this kind of plugin extension system, and it's very cool that that's not just something you're using as an option, but sort of as the extension model. Very, very exciting. Now my question is, what do you think are right now the biggest limitations that you wish didn't exist?
I wish people could write, this might segue well into the next presenter, but write extensions in TypeScript. That would be my ideal, like, or Python or some language that has a little bit less of a learning curve than Rust, like yeah, TypeScript, Python, Lua, something like that, and have that work efficiently. I think I tried componentize-js a while ago and ended up with, I think it would be too big of a binary for us to recommend people doing that, but that's definitely a project that I follow with interest, like, because if people could write, that's kind of the main big sacrifice that we incurred by going with this is, I think, to write extensions, which for us is great because we wanted to be a mono language company and we wanted to just code Rust even when we were developing extensions. So it's not a huge problem, but I would love for people in the community to be able to write TypeScript extensions specifically would be my #1 thing.
Well, you'll be in luck soon.
Yes, Taylor, I see you have a question.
Yeah, so related to that, have you had anyone have success writing in any of the other languages that do have decent support, like Go, or at least Tiny Go, and or any of the other types of things out there, or has it pretty much been Rust that people have been building it in?
Yeah, so right now, yeah, Rust is the only thing that we theoretically support. I think if someone actually in theory, someone could go and set up some other language that has support for Wasm and the Wasm component model and get it to work. I don't think anyone's tried doing that. I think I've seen some people who have been trying. I think someone was trying to get Zig working, but they were kind of going at it for they didn't sort of realize how deep the problem was. They were sort of just trying to take some Zig, compile it to Wasm, and we're expecting to just sort of load that that Wasm bundle and have it work. But then I explained to them that there's sort of all these other things, and we also have there's other things we're providing at the Rust language level. So for example, the for reading settings in an extension over the wire, we actually just represent them as JSON strings. That's kind of what we're passing back and forth is the serialized JSON representation in WIT. But then in our our Rust extension crate, we actually have some Serde types that people can then use. And so then we do a bit of, so the extension authors aren't kind of directly working with that low level WIT API to read the settings. We provide a higher level API that speaks impl, serialize, deserialize. And so that's something that people would have to then re-implement if they were using another language. Yes, I see we have another question.
Max, you mentioned componentize-js binaries were too large for you to recommend. First question, what is that maximum size that you feel comfortable recommending to people? And is that limit because of bytes downloaded over the wire? Is that instantiation time? What is the main factor there in recommending the maximum size?
Good question. I don't know. I guess just people intuitively, if you were downloading an editor plugin, what would you think would be maybe it's a question. It's a question for I as the implementer of the plugin system maybe shouldn't be the one to, but I don't know. I kind of think I would expect a plugin to be, especially if all it does right now, all Zed plugins do are install language servers and sort of adapt their output to Zed's style. They format auto completions to look nice and stuff like that. And so it's very limited. And so I don't know, I wouldn't think that they'd be more than a megabyte. I think I was getting like a 10 megabyte binary with componentize-js or something like that.
So we are working towards something, and I can expand a little bit on that in the next presentation, on something that for your use case should actually enable you to ship a build of the JavaScript runtime with Z, or have it as a dependency for individual plugins, and then the individual plugins can just be JavaScript files. No Wasm files at all. And then you load them at runtime into the Wasm binary, and it runs as in the Wasm sandbox.
That'd be amazing for us. Yeah, I would definitely recommend that to extension authors.
Awesome. Thank you so much. We are nearing in on the time here. Marshall and Max, you have a lot of folks here that are listening to what you're saying and are very interested in helping you to achieve these goals. We are appreciative of the work that you have done, and it's really, really cool. So thank you so much for joining us today. Next on the agenda, we have Tomasz, Guy, Till, and Victor. We have the entire crew coming in here for talking about SpiderMonkey.js and Wasm ecosystem. So if you all are so kind, please say hi and let's talk about some JavaScript and TypeScript.
Yeah, should I share my screen? We have some slides. Can you see that? Yes. Okay, cool. Yeah.
Yeah.
So I think, Till can kick off this presentation, and yeah, we will jump in, and yeah, it's gonna be fun. So stage is yours, Till.
Thanks, Tomasz. And for the record, Tomasz organized all of this, put together the slides here, and unfortunately is a bit under the weather today, so I'm kind of covering for him. Otherwise, Tomasz would talk through this, the StarlingMonkey part, and then I'll hand it off to Guy for some of the componentize.js and some of the Jco parts. So I started the StarlingMonkey project in the Bytecode Alliance as sort of a big refactoring of much of the pieces that existed in Fastly's WebAssembly targeting JavaScript runtime, JS compute runtime, and it's a largely C++ code base embedding Firefox's JavaScript engine, SpiderMonkey. It is a Bytecode Alliance hosted project, and it's really, it doesn't even compile to native code right now. I think that is something we should eventually fix, but the key point is it is very much focused on targeting the component model, targeting WASI, though it doesn't technically need to target the component model. And in fact, there is an embedding of Starling. So it's sort of recursive. I just said it started out as a reimagining of all the parts of the JS compute runtime taken and kind of put together in a different way. And by now, the JS compute runtime is embedding StarlingMonkey. Guy kind of took those parts and integrated them in a different way. And that isn't currently targeting the component model yet. So it compiles to core WebAssembly and can work with that, because one of the goals in the design is to have everything be highly modular, meaning there's a core runtime, which is pretty small. And then there is a header file that abstracts all the interactions with the outside world. And that can be implemented in terms of WASI, or we have an implementation in terms of multiple versions of WASI P2. And Fastly are maintaining a version implemented in terms of Fastly's compute ABI. And a lot of the built-ins are shared. I'll get back to built-ins in a moment, but not all of them. So notably, the implementation of fetch and request responses and so on is not shared because the differences are a bit between the host APIs were too big for it to kind of be an easy transfer. But that's where the modularity comes in. It's a kind of regrettably, but best I could come up with, CMake-based build setup that allows you to say, use this built-in, don't use this one, but use this other one. And so in Fastly's embedding, all the built-ins that made sense to use from upstream from StarlingMonkey are used. And then the other ones and additional ones that are specific to Fastly are added and live in their own repository, also open source. We are, so I work at Fermion. We have been using this in production since, I don't know, sometime last fall. And I guess Fastly also a similar time frame. I know others are using it. In general, there's nothing specific here. So StarlingMonkey purely targets WASI P2 APIs. It works, or the output works in all WASI P2 environments. And in fact, I do all my testing with it just in Wasm time. And then additionally, we at Fermion have an SDK built on top of it and on top of componentize-js that also exposes additional bindings for spin our runtime specific things. So spin CNCF project that embeds Wasm time and adds additional APIs. But I know that StarlingMonkey is not just used in these two environments, but also other people are using it, other people are documenting how to use it in their environments. And it's decidedly meant to always be fully focused on standards. And not just on the side of where it runs, but also on the side of the APIs it makes available. And I think Tomasz, I forget, unfortunately, whether that's covered on a next slide. So yeah, here we can see some of how it works. It's the entire SpiderMonkey C++ and Rust-based JavaScript engine compiled to WebAssembly, and then additionally at runtime, StarlingMonkey built around it, and then a lot of web built-ins added as implementations. So SpiderMonkey comes with built-ins that are specified as part of the JavaScript standard in TC79 and nothing else. And StarlingMonkey adds fundamental things like an event loop, things that you need to even be able to use promises at all, and anything async, but also all fetch, request responses, text encoder, decoder, a streams implementation, so readable, writable streams, and a whole bunch of additional things, and that I know is on a future slide. But the key part here is all of this runs inside the linear memory of a WebAssembly instance, and hence tightly controlled. We don't have the whole C++ code base of SpiderMonkey and whatever we do in StarlingMonkey as part of the trusted compute base. This is all still inside of Wasm time or whichever other WebAssembly runtime it's running in. Can you move to the next slide? So that also means it's interpreted. We don't have jitting. How do we make this fast? There are two parts. The first one's on this slide, which is we make startup incredibly fast. In fact, faster than any native runtime can match. It's sort of we're basically we start running while others are tying their shoelaces by having our shoes already fully ready, and we are ready to hit the ground running. We do this by loading the JavaScript file and then running the top level script before we deploy. And then we take a snapshot of the heap, which is incredibly hard for natively running code, but very easy for WebAssembly. And this, again, is not a proprietary thing. WASI is a tool that does this and emits a new WebAssembly file that can run wherever you can run WebAssembly, and has this heap state baked in. And then when an actual instance for runtime execution is created and some event comes in, for example, in the case of Fastly's use case or Fermion's as well, a serverless HTTP request, then we do almost no work at all before running the first line of JavaScript in that event handler. And that means we are really within microseconds. We are running code reacting to this handler. We do not have code startups basically ever after that thing is deployed. And you often hear kind of claims of no code start under 5 milliseconds. For most HTTP events in a lot of kind of use cases, 5 milliseconds, we've long shut down again in 5 milliseconds, because what you're doing for each of the incoming requests is trivial compared to starting up the runtime and so on. And so we can basically say, yeah, if you're not doing very heavy compute in your JavaScript, then this is faster than native runtimes could be, while we giving you a fresh instance every time, and while not incurring startup costs and so on at for a request if you haven't done one or served one on this node before. So that's WASI, and the second part is on the next slide. Weval is a so basically what we can do in addition is the interpreter that SpiderMonkey has, in addition to different JIT tiers. What we can do there is we can sort of partially evaluate it and turn it into machine code optimized for the code it is evaluating for this particular JavaScript application. This is a pre-processing step. It doesn't work for all use cases, same as WASI doesn't work for all use cases. So Max and Marshall, for your use case where I just said earlier, you can load the JavaScript file at runtime, these things wouldn't apply. But for serverless use cases in particular, where you have a deployment step before doing anything at all, you can do this before deploying or as part of the deployment process. In this case, you don't just take a snapshot of the heap state after evaluating the top level code. You also emit a WASM file that contains optimized code for, instead of the interpreter, it contains machine code that's basically the interpreter applied to the interpreted code. And it has pretty decent results, 2.5 to 3x speedups. This is shockingly consistent across different use cases, and is available right now. There's more potential for more optimizations by actually using types, it doesn't have that much overhead in terms of seeing your comment max. It's not that much bigger. Yes, it is bigger, but in particular, once you talk about compressed binaries, it's not a preposterous amount of additional code size. In general, code size is surprisingly not something we've been focusing too much on, because for a lot of use cases, there are more urgent things and have been more urgent things for years. But there is all kinds of potential for optimizing it. The most notable one being we should not have to ship all of SpiderMonkey with every component that uses it. Instead, we should be able to say, here's a WASM file containing SpiderMonkey or all of StarlingMonkey. Here's a WASM file containing kind of the snapshot, and that loads the StarlingMonkey build at instantiation time and doesn't duplicate it. We know how to do it. It's engineering work to do it. It's not research anymore. It's yeah, we have to do it, and we have to be able to prioritize it. But so overall, we are throughput-wise, if you do heavy compute in JavaScript, we are quite a bit slower than a top-tier JIT compiling engine, such as SpiderMonkey itself, or V8, or JSC in Safari. For a lot of use cases, that is totally fine. For other, and in general, the component model gives us sort of an out by saying, well, if you're doing heavy compute in JavaScript, maybe don't do that. Do it in a language that's better suited for it, and focus on the sort of the high developer investment, low compute time glue parts that JavaScript is actually excellent at. Let's go to the next slide.
One thing I wanted to mention also regarding the binary size, I think that with Weval, there is also a lot of potential to eliminate, like use Weval to eliminate like dead code, because this is what basically we are treating the JavaScript code as a constant, and what Weval is doing is propagating the constants through the WebAssembly, basically, right? So there is a lot of potential to dead code elimination in Weval still, and reduce the binary size, I guess.
That's actually a great point. Yes, that it's not purely addition, or right now it is additional code, but we could use it to then do a lot of cleanup in the engine of parts that are now not longer needed. In general, StarlingMonkey or the SpiderMonkey, the JavaScript build of, sorry, the WebAssembly build of the SpiderMonkey contains a lot of code that we know will never be executed. It's built system work to turn it off, basically. For example, all the object model parts of the WebAssembly support that SpiderMonkey has are still there, even though it doesn't contain a WebAssembly engine, because that wouldn't make any sense. A lot of stuff is still compiled in. That's probably a few hundred kilobytes of code. So engineering work and priorities, basically. So yes, Winter TC is a standardization effort basically for interoperable JavaScript environments outside of the browser. Winter is for web interoperability, and TC, technical committee of the JavaScript standardization body. This is a list of kind of all the built-ins identified there as being needed for good interoperability. We're doing pretty well on that. Actually, the last few months, Tomasz has done amazing work to get us to support a lot more of these built-ins. So we're doing really quite well there. Streams and crypto will be holdouts to some degree. It'll take a while longer until we're fully up to spec there. But the goal is, on the next slide, to actually get to full compatibility there. And then another big thing is debugging support. I have that working, but not production quality, to have breakpoint debugging based on the debugger adapter protocol, including post-deployment in whatever environment you're running. No changes needed. All you need to have is socket support as part of WASI P2. Then over time, yeah, it should become more and more of a Rust runtime, and WASI P3 async support with good integration with other components in using async. So being able to use an async API exposed by, or a stream, for example, exposed by a Rust component in JavaScript, and have it be represented as a readable stream in a efficient and pluggable manner in as part of a processing pipeline. That's a big upcoming thing, big push for us in the component ecosystem in general, and one of the focus areas for us right now. And Guy, if that's okay, I'll hand it off to you for the componentize-js part.
All right, thanks, Till. Yeah, so there's a huge amount of pieces here. The StarlingMonkey project has been an incredible sort of simplification for us at Fastly, being able to share a lot of the foundational pieces of the engine and the compat story and all of the new developments that are happening in a sort of a project that can be used in as many ways as possible. Componentize-js is a separate project to StarlingMonkey, which basically fulfills the use case of wanting to create components that are built to a specific WIT world for any type of sort of plugin or extension system, similar to kind of like the Z extension system, where you're embedding to a specific world. The default world in StarlingMonkey today is the HTTP server proxy world. So you are exporting an incoming handler, and you're importing potentially all of preview 2. The componentize-js workflow is, instead of that, where you pass a JS source and you just have a server handler, and it's kind of like the standard service worker kind of event model. You want to pass a WIT world in, and then some JavaScript module that fits the same shape as this WIT world. And the idea with that translation layer is that we follow the same bindgen rules that the Jacobs project uses when you are running components themselves in JavaScript. So we have this kind of like bidirectional transitivity on the bindgen. So the same bindgen you would do when running JavaScript components in a JavaScript environment, you would also do the mirror bindgen of that. For the most part, there are some exceptions when creating a component from JavaScript, so that the shape of the module feels much the same, whether you're writing a component or consuming a component on the guest server sites. And one of the changes is the imports become the exact world scoped imports. So you import WASI : another one of the changes is that when you write your functions in componentize.js, you can write async functions which get syncified because we control the event loop inside the JS engine. So you can actually export all functions as asynchronous if you want, even though the WIT world represents synchronous. Preview 3 support should also allow that to run on Preview 3 async, but that support is still coming. So at the end of it, what you get is a component that has the JavaScript that you pass, that WIT world, and it's got an interface that then exactly matches the WIT world that you passed, down to potentially some Preview 2 imports for StarlingMonkey features that might also be needed. And for that, we do have a feature called features. So you can enable and disable features in componentize.js, which will actually disable Preview 2 imports so that you can create fully pure components. We don't do that by default because otherwise you get no debugging information when you get a panic. But you end up with a component exactly representing the interface that you want to target. Adding support to this for better debugging should also be coming with the work that Till is doing, where we can actually support composing that world with the debug adapter, which I believe is just a Preview 2 sockets API, and potentially some environment variables. And recently, in the most recent release of componentize.js, Till's work already on getting better debugging build outputs has allowed us to at least now get stack traces in componentize.js, which sounds like a small thing, but it was great to release last week. I think that's most of what I want to say on componentize.js for now. Oh, one other thing. In terms of the StarlingMonkey TypeScript story, I think ideally we would support TypeScript out of the box, and it would just be a full TypeScript experience. We have a tracking issue for that. One of the difficulties there is that, like, we do just at the moment encourage with both componentize.js and StarlingMonkey, for the most part, run a bundling step before you use these. So you can put it through your standard JS bundler, ES build, or whatever you're using, and then run that in StarlingMonkey or componentize.js. But we are trying to replicate those semantics as well in projects. So StarlingMonkey actually has a full module resolver that should mirror the Node.js module resolver in future. And ideally, it would also support the TypeScript support, at least for type stripping or something like that, so that we could do that all on the StarlingMonkey side, and even provide proper stack traces directly from the engine, which would be really nice to be able to do. And the dead code elimination we've been talking about would also be useful with the TypeScript work, because we don't want to be including an entire TypeScript parser in the in StarlingMonkey and add another. I think TypeScript's 2 megabytes or something, or more. Another megabyte or 2 to the build. So we would need the dead code elimination in that wiser step to be able to really push into that workflow. But it would be great to see that in future as well. So the Jco project is kind of the other side of the coin. It's designed to be a kind of a multi-purpose tool chain for JavaScript developers working with components. So it's a full JS native ecosystem. You can npm install it. You're not going to have native builds and native dependencies. It could sort of self-hosts with its own component builds. So you can run Jco transpile, and this is the main command that it offers, which is supporting components, running components in JavaScript environments, so browsers, your kind of workers environments, and your Node.js environments. And so Jco transpile takes a component and outputs a directory of modules with a main module entry point, whose module interface represents the WIT world that was targeted by that component. So it's called transpilation in the sense that it's represents that component in JavaScript semantics as if it were supported as a JavaScript module. And underneath it's just bindgen. So it's just like we're doing guest bindgen in componentize.js, Jco is just doing host bindgen, and it's just generating a bunch of JavaScript and core WebAssembly and adapters and trampolines to implement out the full component model semantics in it on top of basically Node.js at the moment. Browser support for Preview 2 is still very limited. There is a bunch of work on better asynchify support and the Preview 3 work, which is going to unlock that soon, hopefully. And then there is also a componentize a command in Jco, because the componentize.js project doesn't have its own CLI. In future, componentize.js might merge into StarlingMonkey or a lower level project. And if StarlingMonkey were to get its own CLI, it might move there. But for now, it remains in the Jco project. And another interesting development in the project has been the WebIDL support layer, which is still experimental. But Mendy has been doing a bunch of work on supporting a WebIDL to WIT conversion tool. And we support that in Jco, actually, where you can actually have a workflow where you take a WebIDL set of documents, create a WIT world, and without needing to do any bindgen, we have this kind of like smart intrinsic that's able to know how to read that WebIDL WIT file using some special sort of IDL conventions and say, well, since you've described the IDL, we can just access those things directly off the JavaScript global object. And so there's some really, really interesting workflows around that where you can just go straight from IDL to writing JS code against that generated WITs, and then just running it in a JS engine if it uses these special IDL, basically import patterns, specific IDL convention in the WIT import style. That is still highly experimental, but I think a really, really interesting direction for the project at the moment, on top of all the Preview 3 stuff, of course. So yeah, that's kind of it on the toolchain side. So if anyone has any questions for any of us, Tomasz has been doing a bunch of work on StarlingMonkey and compatibility, and so yeah, and anything between all of these, we're happy to answer questions. Or if there's no questions, I guess we are also at time, so that's fine too.
We are close on time. Actually, we were over by a minute. Could you add a link to the slides to the meeting, the doc?
Sure, I will.
Thank you. Thank you so much. Anybody have any questions?
I have questions. I know we're close to time, but I was curious about sort of the trade-offs versus in like the design that Till mentioned earlier about kind of shipping the StarlingMonkey Wasm file separately from kind of the actual JavaScript code versus the approach where that's more leveraging Wiser and kind of partial evaluation. I guess like what applications for my own use case, I don't know which would it be better, honestly. I just like, I think you kind of have a sense of what it's like we sort of want to ship a small bundle that users can download conveniently, but I think it doesn't need to be super fast in terms of compute. But so what use cases seem like better for kind of shipping the JavaScript source code versus doing Wiser and stuff?
You should absolutely ship the source code. And I think for your use case, you kind of can have your cake and eat it too in all regards, because I'm not saying you can ship this tomorrow. There's work to be done on the StarlingMonkey and componentize.js side, and then you would have to do some work for bundling things, but it's all not far off. I think the ideal setup for you would be, actually, no, for the ideal setup, there wouldn't be too much work on our side to be done. Ideally, what you would do is ship the toolchain, including weval, and so weval basically replaces Wiser. It does both this ahead of time compilation, the partial application of the interpreter, and taking the snapshot. And ideally, what you would do is have a baseline JavaScript support layer that contains this, and then individual JavaScript plugins can be shipped as JavaScript files, and as part of loading them, you run them through weval, you get out a Wasm file, and then you store that on disk. And then you can load it and have it execute kind of as fast as we can execute and have the initial snapshot taken. I think that makes most sense. Otherwise, if you want to have things be as small as possible, also on the user's machine and so on, then you can always do at load time, just instantiate a blank StarlingMonkey build, load the code, and then you probably don't want to terminate it immediately again, and you probably want to keep it instantiated and be able to continue calling exports on it. And in that case, you don't need snapshots. You have the startup cost once, and it's fine. The Wiser thing is optimized for serverless environments where you don't want to have cold starts, but I think that's less of an issue for you.
Yeah, we can carry the instance as state in a long-lived way. That's very cool. Yeah, thank you guys so much for explaining that.
And we are more than happy to answer questions and on how to implement these things as needed.
Awesome. Any other questions out there?
I guess I'll only mention that if you have questions, we have StarlingMonkey channel on Zulip, so that will be a good place to get with the questions.
Great.
Excellent.
Okay. Yeah,
Excellent.
we'll find you in there.
That's under Bytecode Alliance, StarlingMonkey. Yeah.
Yeah.
Awesome.
Also, I've dropped a link to Jaco in the chat. Sorry, in the document, in the notes for the meeting, so it should be easy for everyone to find.
Awesome. Thank you so much, everybody. Till, Guy, Victor, especially, thank you for taking notes. Tomasz, you all have been awesome. I really appreciate the presenters today. I hope everybody found this meeting informative. I will post the link with the video shortly. I just want to say thank you again, and I hope you all have a fantastic day. Without any further ado, we can adjourn for today, and hopefully see you all back again soon.
Thank you for having us,
Bye-bye.
David.
All right.
Thanks, y'all.
Everyone.